All right, hey everyone. Thanks for joining me on week 3 of HPC in the cloud. I'm Joe Schoonover from Fluid Numerics, and I am out here in Boulder, Colorado today. We're going to be going over a few different strategies for managing Python packages on an elastic HPC cluster on Google Cloud today. So if you missed the last couple weeks, there are a few things you'll want to do to get started if you wanted to follow along with the tutorial. So if you're not already on Google Cloud, definitely go ahead and create an account at console.cloud.google.com. If this is your first time signing up, you'll be able to get $300 trial credit. You can use your Gmail account or a G Suite account if your organization will allow you to do that. The other thing is you'll need a Fluid-Slurm-GCP cluster. This is a click to deploy solution on Google Cloud that will get you set up with a login node and a controller that will host the Slurm job scheduler, much like a very typical HPC cluster, except that it's all going to be run on Google Cloud. So you can find out how to do that by looking at our help pages, help.fluidnumerics.com/slurmgcp. So once you go through that and you get yourself set up, you'll be ready to follow along for today. And what we're going to do is look at, like I said, 3 different strategies for managing Python packages. And I've broken them down into these 3 sort of categories here for you. The first one we're going to look at is what I call a centralized approach, where you can install your Python packages into one location that's really maintained by like a system administrator, and we want to basically make those accessible to everyone on the cluster. So we'll show you how to do that using some of the environment modules that are available on Fluid-Slurm-GCP, and then kind of highlight why we have to do it this way as we go through it. Now, the other 2 approaches, the decentralized approach and the containerized approach, put the control of package management, dependency management into the hands of your developers. Neither of them will require root access on the cluster, which is nice. In the virtual environments setup, just to give you a short overview, essentially you're going to be able to install your Python packages in your home directory, which makes them available to all the compute instances across your cluster. But again, it allows your developers to control what packages they need for their applications. Now, the last approach, by far my favorite approach because it applies to more than just Python, is the containerized approach. So I'll show you how to use Google Cloudbuild to create Docker images and store those in Google Container Registry and then pull those into your cluster with Singularity. So we're going to go ahead and just jump right in. What we're going to do first is SSH into your cluster, into the login node, and you can clone this repository we prepared for you. And once I get it cloned up there, we'll walk through what we have available. Let me go ahead and just copy my login node's IP address and jump right in. So if this is your first time seeing the cluster, I'll just give you a quick tour of what's going on here. So I'm on the login node. Up on the top left of my screen here that I'm sharing with you is the Google Cloud or the Google Compute Engine user interface, and you see I've got 2 virtual machines there. One's the login, one's the controller. The login node is where I've just SSH'd into. The controller actually hosts the home directory. So if I just show you my mounts here, I've got home, and I've got a directory called apps that's actually being hosted by that controller. The controller also hosts the Slurm job scheduler and some of the other tools that are available. So if you run sinfo, if you've been on a Slurm cluster before, you might already know many of the Slurm commands. You can see I've got 1 compute partition already ready to go, and the nodes are in this idle tilde state. And the tilde just represents that they are what are called cloud nodes. So the scheduler actually knows, hey, I can basically spin up these compute nodes as needed on the fly. Okay, so we're on the login node. Let's go ahead and clone this repository. And we all that's in here is just a simple little bit of code that's just going to load Matplotlib, Scipy, NumPy, and TensorFlow, and then report the versions of each of those packages and the location that they're installed in. So just give me 1 second here and I'll show you how that works. Okay, so let's check out that directory. All right, so if you look at test.py, this is the main application we're going to be running today. All it does is it brings in, like I said, Scipy, NumPy, Matplotlib, and TensorFlow. And for each of those packages, it's going to report the version and the location of where those packages are installed. And the reason why I'm doing this is because as we go through these 3 different approaches, the containerized approach, the centralized approach, and the decentralized approach, you'll see different paths show up for where these packages are actually made available. Now, the whole reason I'm actually going through this demo with you today is to point out something that I've seen trip up a lot of folks who use our clusters. And you'll notice when you get on the cluster, hey, I know there's Python 3 already available, so why are we doing anything crazy? Well, if you were to run which in front of Python 3, it'll tell you the path to that installation. You can see it's under user bin. Now the deal is user bin is a directory that right now, since I'm on the login node, it's a directory that's only visible in the login node. So if I were to say do my package installations with pip3, it's going to use user bin pip3, which means that all the packages that are installed are going to be installed under user bin. And the problem with that is when you launch a job and you spin up the compute nodes won't have access to those packages because they're only installed on the login node. I guess what we did as a first solution here was to provide environment modules that have Python 3, and we also have Python 2 in case you still have applications that are in Python 2 underneath this apps directory. Now, apps is a directory just like home. It's NFS mounted across your entire cluster. So again, the controller by default hosts the apps directory. When compute nodes are spun up and brought online, those compute nodes also have access to both apps and home. So if you install things underneath apps, they'll all be available there. If you haven't used environment modules before, what I just did there was a command called module avail. It'll show you the modules that you have on this cluster. And in the later episodes of this this set of tutorials here, we'll talk a little bit more about writing your own environment modules. But today we're just going to look at using the Python 3 modules. Let me go ahead and jump over to the next slide here. And what we're going to do is just go through a little bit of a demonstration of how the centralized package management works. Now, if you're going to install Python packages underneath the apps directory, you will need to be root. So let's go ahead and run sudo su, become the root user. And once you're the root user, go ahead and do a module load, Python 3.8.2. Okay, so now if I run which Python, actually I'll run which Python 3, you can see now it's actually using apps Python 3.8.2. And if I did which pip3, you can see it's also using the pip3 underneath that apps location. Whoop, looks like I just dropped my terminal. Let me fix that real quick. Okay, there we are. Okay, so if you're root and you've loaded this module, we can run pip3 install Scipy, Matplotlib, NumPy, and TensorFlow. So if you have applications that are using these packages, this is this is one way we could handle. I did not spell Matplotlib correctly. There we go. This is just one way you can handle your packages here. And what's going to happen next, once these packages are installed, we're going to run a Slurm batch job that will run that test.py application on a compute node. And what's going to show up on the screen is which Python 3 binary it's actually going to use, and then the locations of each of these packages we're now installing. So we'll give it a quick minute here. Okay. It's going to take another minute here to finish up installing. Yeah, sometimes this TensorFlow package can take a while. You know what? I'm going to kill that. I'm going to do this without TensorFlow for today. All right. So if you decided to do what I just did there and remove the TensorFlow, just go into that test.py application and comment that out. And that's just really for the sake of time today. Let's take a look at this batch file that we're going to use here. So essentially, to run jobs on the Slurm cluster, you'll need to use either srun or sbatch, or a combination of those with salloc. We're going to use sbatch today. So make sure when you go to submit this file, you open this up and you set your Slurm account correctly. Mine is just demo account, and you set your partition to be the partition you want to submit the job to. So what's going to happen is when this job runs, it's going to use environment modules. First, it's going to clear any environment modules that might be already loaded on this system for your account. It's just a safe thing to do. We're going to load Python 3.8. We're going to ask it which Python 3 to make sure we're running the correct Python 3, and then it's going to run. This should just be test.py. I'll have to correct that in the repository, so the next time you guys download this, it won't be an issue. All right, so if I look at that test.py, again, remember it's just going to print the version in the file for each of those packages, and we should be good to go. So I'm going to go ahead and just run sbatch. Oh, make sure I'm not root anymore. That will be a problem. We'll do sbatch test.batch. Okay, so it submitted the job. So if you run sq, you can see we got job ID number 2. It's running in the demo partition. The name of the job is just the name of the batch script here, since I didn't give it a name inside the batch script. And the status is CF, which stands for configuring. And what I'm going to do down here is just put that sq command on. Actually, before I do that, if you were to look at sinfo, you'll see a listing of those compute nodes again, and now you see that demo partition 0 is in this alloc # state, and the # means that it's in a power up mode. So if you missed the tutorial last week, the short end of what we illustrated last week was that basically you have access to an auto scaling cluster, and what that means is compute nodes are created as needed when you submit jobs, and then they're taken down when they're idle for too long. And the default settings for that is 5 minutes. So if we let the node just sit there after running this job for 5 minutes, the Slurm controller daemon will take care of spinning that down for us. Now I'm going to go ahead and put this on watch here. I'm going to refresh the Google console, and you'll see that that compute node is actually coming online. So essentially, controllers issued the calls to Google, hey, can you give me a compute node? That compute node's spinning up using some virtual machine images that we've created for this solution. And basically we're waiting for the Slurm daemon. Well, there's a startup script that runs, and we're waiting for a Slurm daemon to register with the controller to say, hey, I'm here, I'm awake, and I'm ready to do some work. We've seen variations in the spin up time, everything from 30 seconds up to a couple minutes. The nice thing is if those nodes continue to stay live and you can keep them busy, jobs will go through right away. And it looks like our job did go through. So when the job's finished running, if you notice in that test.batch file, we set the -o flag, which stands for standard out, and -e flag, which stands for standard error, to this file called test.out. So we can take a look at test.out. And you could see, okay, so which Python is it using? Well, it's using apps Python, right? And that's, again, we set this cluster up so that apps is mounted to those compute nodes when they come online, so you'll always have access to anything installed underneath apps. And you can see the Scipy it's using and NumPy are both underneath apps as well. Same thing with Matplotlib. So that's centralized package management. Now the downside, again, with this approach is whoever's doing the installation has to go root. Now, if you want to run your cluster in a way where you do have this sort of centralized system administration approach to how you handle your packages, this is perfectly fine. Now, if you wanted to go a route where you said, hey, look, as a system administrator, I just want to provide you access to Python. I don't necessarily want to have to keep track of all the different research teams' application dependencies. This is where a decentralized approach actually works out quite well. And I really think containerization is decentralized itself. But it's a little bit of another animal in terms of how it changes your workflow as a developer. So we'll start off first with something kind of in between there where we're going to use virtual environments. Now, as a user on the system who's not going to escalate to root privileges, you can use virtual environments after loading the Python 3.8 module. So we'll start there. Module load Python 3.8.2, and then we'll use the Python 3 venv package. So this is virtual environment, and the argument we're going to give to it is env. And what's going to happen is this is going to create a directory called env, where I'm currently at in my home directory. I'll give it a quick second to catch up. And underneath that env directory, you got a pretty typical file system structure. You got bin, include, and lib. And whenever we install Python 3 packages, which let's take a look under bin, you can see we've got pip3 under here. We've got Python 3. So everything is going to be referenced to basically binaries in this directory here. Now to activate that environment, you'll run source env bin activate. And now if you notice, I'm on the left side of my shell prompt, I've got env closed in parentheses. So that's how I know I'm actually in my virtual environment. If you wanted to get out of that virtual environment, you can just run deactivate and you're out of it. I'm going to go ahead and keep it on. And then we're going to do pip3 install Scipy matplotlib. Actually, before I do that, let's do something real quick. Again, which pip3 am I using? I'm using actually this one in my home directory, which is that tilde symbol there, Fluid-Slurm-GCP Python demo. So I'm inside, basically in my current path, basically using pip3 underneath that env directory. Same thing with Python 3. Okay. So now what I'm going to do is just run pip3 install Scipy matplotlib and NumPy. And if you do want to run with TensorFlow here, go ahead and add TensorFlow if you like. Of course, if you're doing this with your own applications as you're following along, that's perfect too. So whatever your package dependencies are. Okay, so we'll let that run for another second. And again, we're going to do the same thing we did before. We're going to run another batch job on the compute nodes. And this time, instead of using, what you'll see is instead of us end up using the installation underneath the apps directory, although I'll still have the apps Python 3.8.2 module loaded, it's going to be using Python 3 underneath my home directory, and then you'll see the locations of Matplotlib, Scipy, and NumPy all point to the package installation locations here. So to do this, we actually have test dot, let's see here, venv batch file for you to test out again. Open that up, modify that account, and partition values. It's doing the same thing, except now when it runs, you have to source that env env bin activate. You need to activate that virtual environment before you actually run your code. So if you're working with virtual environments, if you're not working with them now and you want to work with them in your job submission scripts, make sure you add those statements before running your application, and then put that deactivate in there on the other side of it. So let's go ahead and submit that job. Hopefully I didn't talk too much and the job goes right through. And it did, which is really nice. So if I look at test.out, let me clear my screen here, get a little less cluttered for you. You can see at which Python it's using. It's using now the one underneath my home directory rather than underneath the apps directory. And again, the packages, the package dependency locations are now also underneath that home directory. So that's our decentralized approach. Now let's look at the last one here, is the containerized approach. Now the containerized approach is a little bit of a different story. And generally what we recommend for this kind of workflow is sort of like a develop locally, run on the cloud, right? So what I usually do for a lot of so we develop some applications in-house. And I do a lot of my development on my local workstation here that doesn't have a huge amount of resources, but it's at least able to do some basic things, like I can build the application here and make sure some basic tests are met, and then I can actually use Google Cloudbuild to do some more extensive testing, and then I actually end up using Fluid-Slurm-GCP to run that application in production. So I've kind of got these like three sort of staged environments here, so I can do my development kind of wherever I want to. Once I have an internet connection, if I push that stuff to my Git repository, you can use Google Cloud's build triggers to have things built automatically. And as a artifact of those builds, you can get Docker container images in Google's container registry. And we've included on Fluid-Slurm-GCP Singularity so that you can pull those Docker images onto that cluster and run them. Now, the difference between Singularity and Docker, at least from the runtime perspective, is if you're familiar with Docker, you know that you usually have to have some type of escalated privileges or access to an account with escalated privileges to run Docker containers. With Singularity, that's not the case. So it does mitigate some of these security vulnerabilities that some people are concerned about when you're on like a shared work environment like an HPC cluster, very much like Fluid-Slurm-GCP. So what we're going to do here is, if you're following along, go ahead and log out of that login node and get onto your local system, clone that repository again, and we're going to first go through a process to build a Docker image, and we're going to use Google Cloudbuild to do that. So on your local system, you'll need the Gcloud SDK as well. If you don't have the Gcloud SDK, that's all right. If you look up on the Cloud console, on the top right, there is a button that says Activate Cloud Shell. The icon kind of looks like a little terminal. If you click that, that will open a terminal in your web browser, and you could do all the same work there. All right. So what I'm going to first do is set my project to the project I'm working on. So Cloud HPC demo for me. Okay. So let's take a look at two things in this repository. And if you don't already have stuff like this in your repo, this could give you a good starting point towards getting yourself up for containerization on Google Cloud. So you got two things in here. One is a Docker file. So a Docker file is a recipe for building your application. If you haven't written one before, it's pretty easy to learn. You basically pick an image to start from. You put in the instructions to install your package's dependencies, and then you're pretty much set from there. So this one is pretty straightforward. We're going to start from Python 3.8.2. We're going to pip install. I'm going to go ahead and remove that TensorFlow package just in case it causes some delays on us here. So we're going to pip install our package dependencies, and then we're going to copy the current location source code into the container image underneath a directory called app. The other file that we're going to use, and this is a file specific to Google Cloudbuild, is cloudbuild.yaml. This is just a dictionary that specifies the steps required to build and perhaps test your application. So here's just doing a single step just to build it. You know, if you're doing this for continuous integration purposes, you'd probably have some extra steps in here to actually run some tests on your container. that's created in this process. All it's going to do here is use Docker to build our container. That's pretty much it. We will have some more tutorials that go more in depth on using Cloudbuild for a variety of things, and we will start covering testing and stuff like that. But for today, keeping it pretty simple. Once you have both of those in your repository, a Docker file and a Cloudbuild file, you can run gcloud builds submit. Now, normally in practice, what you would do is set up build triggers that are tied to your repository. Maybe you have like a specifically named branch or different tags that you want to have trigger builds, or maybe you want to open a pull request and have that trigger build. Google Cloudbuild can basically be told to run on all those types of events. Of course, you can also manually trigger like we're doing today, but in practice, usually you'll set up those build triggers. And all you can focus on is just coding and submit the code to your repository. And let's take a look at the Google Cloudbuild dashboard. So if you went over to products and services menu on the top, look down for Cloudbuild. On the history, you'll see basically a summary of pass fails for all the builds that have happened in your Google Cloud project. If you click through on a specific build, like the one we're running right now, you can see there's all the logs, everything that's happening on that system is being piped back here. Now, the cool thing about Cloudbuild is everything is run on isolated environments, so you don't have to worry about anyone basically requiring to have root escalation on shared resources, stuff like that. This is done in an isolated, secure environment for you, so you can basically in your Docker files, pretend like you have access to basically install things at the operating system level. And here we go. This is looking like it's done. And what happens here at the other side of this, once the build is done, when we are working with Docker images, those get posted to the container registry. So if you go down to Tools, and from that Products and Services menu, here we are, Container Registry. You can see now I've got an image there for Python demo Slurm-GCP. The visibility is set to private. So by default, all your images are secured through identity and access management policies. These are policies that grant or gate access to different things you create on Google Cloud. Here you can see I've actually baked multiple versions of this image. So if you are, if you have some tagging conventions to handle version releases of your application, it can handle all that like any other container registry can. What we're going to do now is use Singularity to pull this Docker container image onto the cluster, and I'll show you how you can run it there. So what I'm going to do is go back to our Compute Engine panel. Okay, so what we want to do from here is go ahead and SSH back into that login node. And the first thing you're going to want to do is basically set up how Singularity is going, or really underneath the hood Docker, how those two are going to handle authentication. Because essentially you just need to be able to have access to that private container image. And we've set up everything so that out of the box, when you deploy from Marketplace, the service accounts and the compute instances that are created all have access to pull those images. So anyways, what we're going to do is run Gcloud Auth configure Docker, and this will just set up a credentials handler file in your home directory. Just give it a minute to run there. Yes, I want to continue. Okay, and then what we're going to do is module load Singularity. And if you just ran Singularity version, you could see right now we're working with version 3.2. And we do regularly go in here and we will keep these versions up to date for you. So awesome. What we're going to do now is run Singularity pull Docker. And then you're going to give it the path to that container. So it's in the Google Container Registry, so gcr.io. You'll give it the project name. So actually, we're doing Cloud HPC demo today for me. So whatever for you, you'll insert your project ID there. So we'll do Python demo Slurm-GCP, and we'll pull the latest version. Okay. So what Singularity is going to do here is go to that container registry, get the Docker container image, and convert it to a Singularity image file. And once that's done, we're going to run a job with Singularity using that Singularity image and basically show the same things we were doing before. Show which Python we were running with and where the packages are installed. Now, if you're not used to containerization, this can be a little weird at first, but the paths that it's going to throw out are not the paths on the host system. They're actually paths inside of the container image itself. And that can be a little weird to wrap your head around if this is your first time working with containers, but trust me, the more you do it, the more intuitive it becomes and the easier it gets. Part of the reason we love the containerization approach is for our applications, like self-fluids, is it gives us the ability to have a reproducible environment in which we can build our application every time, and we can run those tests across a variety of architectures. We build things so that they can run on single GPU, multi GPU, no GPU systems. It's like MPI only. Once we create those container images, we can subject them to the same sort of tests and have a really good understanding of how our applications perform across a variety of hardware, what compatibility issues there might be with different hardware components, and of course being able to just have it all, once you're integrated with Cloudbuild, kind of just done for you automatically, and you're collecting all that information. You can just focus on developing your application and making adjustments from all the data that comes out from just having that work automated for you. It's kind of nice. All right, so we have our CIF file, Singularity image file. And right now it's in my home directory. I'm actually going to go ahead and move this into that Fluid-Slurm-GCP Python demo directory. Okay, and we're going to use the test.singularity.batch file. Again, make sure that account and partition are correct. Now you can see the thing that's different here as opposed to the other approaches is we're actually prefixing everything with Singularity run. We're going to give it the Singularity image file, and then we can run the commands inside of there. So which Python, and then we'll run Python 3. And this time we're referencing app. And that /app directory is actually app inside the container image where we copied our source code. So let's go ahead and run that. Okay. Again, I might have waited too long this time, so we got to wait for this node to come back online. If I refresh over here, unable to load current page. Yep, I figured that would happen. Give me 1 second here. All right. Hopefully I didn't drop off the YouTube live stream here. All right. I think we're let's get back to that compute engine page and we'll press onwards. There we go. Now our demo partition compute node is live, and let's check on that job. Looks like the job ran. So if we look at test.out, Oh, right. I need to, on my local system, rebake that image with TensorFlow. Not there. So, because of the issues with TensorFlow, right now we're getting an error that that TensorFlow can't be found inside the Singularity image. So I'm just going to rebake that. We'll repull the image, and we'll rerun the job. So the nature of doing stuff live. All right. So while we're waiting for some of these things to come up, what else can I tell you here? Let's go take a look at that other cloud build we got going on. All right. Here we go. So I guess if you wanted to learn a little bit more about some of these panels here, everything we can do in Cloudbuild, you could set all like your, so let's talk about your build triggers here while we're waiting for things to come live. A little preview of what we're going to be doing here in the next few weeks. If you have Git repositories on GitHub, Bitbucket, or if you're using Google source repositories, you can create triggers based on events that occur on those repos. So right now, I've actually got no repositories connected inside of here, but there's some pretty easy walkthroughs through these through Google's panels to actually go through and connect all your repositories. And you can see there's different types of events, like I was mentioning. You can push to a branch, push to a new tag, or push a new tag up to your repo. And then if you're on GitHub, you can actually trigger pulls to happen on pull requests, which is kind of nice, because then you get that feedback if you're working on a team and you want to share code or collaborate on code development. It's nice to have tests occur when you're getting ready to merge your code in with someone else's. So that's a little bit about build triggers. I don't want to go too in depth and get carried away here. Looks like we're done there, and the should have posted to the container registry. So let's now get back into that login node. Okay, and we'll go in there again. I'm going to run that Singularity. All right, so we'll do Singularity pull Docker gcr.io cloud HPC demo and Python demo Slurm-GCP and latest. So we'll replace the image we currently have. Oh, right, I need to module load. All right. Okay, so we'll remove that image we currently have and try again. There we go. All right, so it's going to go through that same process one more time. And it's only going to pull down the changes we made to that Docker container image, which is nice. So it should be a little bit quicker this time. And we'll let it write that new Singularity image file. All right, so while we're waiting for that, we'll go ahead and go back to Compute Engine. Yeah, it looks like we still got a compute node, so this should be able to get this job in before that node gets taken down. So I guess while we're waiting, I could tell you another story. So just as an idea of what we've done with some of the information we pull from our build processes. So we maintain an application called Fluids. We're in the midst of a pretty massive refactoring. And every time we build, we collect all sorts of data about every single one of the routines in this code. And we're actually able to take that data as it's created and actually push it off to Google Sheets, and then use another product called Google Data Studio to do a lot of visualization of that output. And it's kind of a neat tool. For our application, we have, close to, I think it's like 96 core routines, and each one of those goes through a number of tests. It totals about 996 tests every time we run. So it's a lot of information to have come in and just try to sift through. Data Studio makes it really nice and easy to kind of aggregate that information and understand how we're doing. If you're interested in that kind of stuff and like really building out CI platforms, feel free to ask some questions on the YouTube chat or reach out to us directly. But it looks like our image is ready. Just want to give you a little story to fill the air here. Okay, we've got our image. Let's go ahead and run that test.singularity.batch, and we should be good. It looks like it's running right away because that compute node's there. Let's take a look at test.out. So these warnings are benign. Inside the container, essentially, there's no group. Like if you don't have consistent groups in your containers as you do on your host system, you'll just see warnings like this. But at any rate, it's using user local bin Python 3, but that's the user local bin inside the container, not on the compute node. And you can see it's also referencing Scipy, NumPy, Matplotlib inside the container. So sorry for the few mess ups there, but like I said, that's how these things go when we're doing live streams. But I'm hoping that this kind of gave you an overview of the 3 different ways you can manage your Python packages. Again, we have the centralized approach where you're doing this all the installation is done underneath apps, usually maintained by a system administrator or a team of system administrators that are managing packages for users. And then we covered virtual environments where developers have the control in their hands to install packages in their home directory with their applications. And then there is this containerization approach, which is applicable to more than just Python applications. It certainly can be a bit more further reaching. Here's some community resources for you. We have a lot of help documentation on our site at help.fluidnumerics.com/slurm-GCP. You can find additional code labs, including a code lab that goes through the stuff we did today in this tutorial. Goes over Python package management. You can find that there at our help site as well. And if you do want to reach out to us at any time, if you're using one of our systems, you just want a little bit of help or some guidance, we're always there ready to help you make the best use of your compute resources that you have available. You can reach us at Fluid-Slurm-GCP at fluidnumerics.com. Of course, I hope you join us again. We do this every Thursday at 4 p.m. Mountain Time and Fridays at 9 a.m. We'll be doing the same episode tomorrow, so if you have friends or colleagues that couldn't make it today but want to catch this material, we'll be doing it again tomorrow, and we'll be hitting this one again next week as well. Coming up in the future, we'll be doing more interesting things with OpenFOAM and peer review, and a few other we got a few other cool things planned before the year is out. So thanks again for joining, and I hope to see you next time.